So this video lesson is all about 3D figures. And it's important to mention before we get started that this terminology of figures is important, whereas what we referred to perhaps as shapes in a 2D world, we cannot refer to 3D things as shapes. Shapes are specifically 2D. So we call them figures. Even though 3D figures may be constructed from 2D shapes, the 3D creations themselves are called figures. Now, we also had another word in 2D shapes called polygon. And any 2D shape that we could call properly a shape that had lines and edges and vertices, we would want it to be closed. But polygons required the extra little bit of having straight edges and no extra intersections of those edges. So we couldn't have something that looks like this hourglass, where the extra intersection was there in the middle, and of course, a circle, although a very fine example of a 2D shape, is not a polygon because it is not made from straight edges. So similarly with any 3D figure, we want a 3D figure to be closed, and that is at least any of the faces that create it are intersecting with each other and don't lend any gaps. But a polyhedron, plural polyhedra here, polygon becomes polygons, polyhedron becomes polyhedra. They require flat faces that are made from polygons, and that there are no extra intersections of faces. Now, this is a bit difficult to imagine, but if you imagine the faces of two soccer balls that were put together and somehow sort of melted together so that the faces intersected all over the place, and inside the two soccer balls there was also the extra faces that were there, that would be an example of something that would not be a polyhedron because of intersecting faces. But more or less, if it's a 3D figure that is closed and created by flat faces and there are no strange intersections, it basically becomes a polyhedron. So let's go ahead and take a look at some 3D shapes. And so to do that, I'm going to go ahead and turn on the camera so you can see me and we can see these shapes. And it's much more fun to be able to look at these shapes on a video screen rather than see them on this 2D plane of the computer board that's here, and not really be able to get a sense for the real depth of them. So there are a number of different types of 3D shapes. We're going to go through them quick. You're going to see some 2D representations on them, some familiar pictures for them, and we're going to talk about some specific parts of them. So the first thing that we have is this idea of a prism. And now a prism can be created from pretty much any shape that's out there, usually from regular 2D shapes, but it's created with a base that is some sort of polygon. That polygon, imagine that polygon is then stretched into 3D space so that the opposite base on a parallel plane, you can see the plane of this rectangular base here is parallel to the plane of this rectangular base here, where all of the other sides are either squares or rectangles. This is an example of a prism. This is a rectangular prism because prisms are classified by what their bases are. Another example of a prism is a triangular prism. Again, a triangular base at the other end, and rectangular faces along the side that connect the two triangular bases. Yet another type of prism built from a hexagon is called a hexagonal prism. And anytime that you get to a polygon that's a pentagon or more sides, you just call it whatever that polygon's name is plus an AL at the end. Hexagonal, pentagonal, octagonal, dodecagonal if you wanted. Again, hexagon, hexagon, and rectangles that connect the two bases in parallel planes. Finally, a prism that is created from a square has a special name. All of the faces here are squares, and we call this a cube. Now, it's very important. A face can be, one of the bases can be a square, but this can be a much longer prism moving forward so that these extra faces, called lateral faces on the side away from the bases, would be rectangles. If they are all squares, though, it is called a cube. So once again, a prism takes a 2D shape, the same base shape in another parallel plane, and uses rectangles to connect the shapes together. This is a prism. If you use a circle, which is not a polygon, to create the prism, then you get what's called a cylinder. And it's the same idea as a prism, and you can see that with this hexagonal prism, it's the same idea. Hexagon at one end is a base, hexagon at the other end as a base, and rectangular faces in between. Except for a cylinder, we start with a circle as one base, a circle as another base, and we connect with what ends up being a smooth, curved surface. Still what's called the lateral curved face, but very similar to a prism, just called a cylinder with the circular bases. Now, if we start with the base shape, and instead of coming to a nice similar base at the other end, it comes to a point, or what is called in 3D shapes an apex, we get what's called a pyramid. So we're starting here with a square as our base, and that square, the figure rather, is becoming smaller and smaller and smaller and smaller until it reaches this vertex here, which is called the apex. The apex is across from the base in a pyramid, which is what this is called. Start with any base, draw edges from each of the vertices of that base that come up to the apex and meet centrally on the base up a little bit, and you get a pyramid. This is called, you guessed it, like in a prism, a square pyramid. This is an example of a triangular pyramid. Both pyramids, but began with different bases. Now, if we had examples of a pyramid that began with a pentagon on the bottom, that would be called a pentagonal pyramid, a hexagonal pyramid, heptagonal pyramid, so on and so forth, just like we were talking about prisms. And as with prisms and cylinders, if you begin the pyramid idea with a circle rather than with a polygon, you end up with a cone. It has the same similar properties, has one shape on the bottom as a base. From the base, well, we see no edges here because edges are the intersections of faces, but the figure gets smaller and smaller and narrower until it reaches the vertex at the top. So pyramid, cone, polygon, circle. And finally, the last figure that I'll mention, I only have an example of a half of it here. But if we have what is more or less a circle turned 3D, if you imagine a ring that you're holding, and you spin, let's say, a quarter. If you spin a coin, what you see, that 3D shape that appears to be where the quarter is spinning, is called a sphere. This is half of a sphere, which is called a hemisphere. But if you imagine this curved surface running all the way around, the same thing underneath it, you can see hemisphere formed from a circle, this would become a sphere. It is actually all of those points in space that are the same distance from the very center of the sphere. That is the definition of a sphere. All points that are equidistant or the same distance from a singular point. Sphere. Notice that this hemisphere has a flat face, which is a circle, but in a regular sphere has no faces, has no vertices. It has no edges where faces come together. So that is the look at a number of the different types of 3D figures that we had. Let's go ahead. We're going to turn off the camera, and we're going to look at some of those 3D shapes just in 2D space. Drawings of them, more or less, because we really can't show 3D figures on a 2D space. And so you can see at the top left here a prism. This one being a hexagonal prism because it has two hexagonal bases. And the rectangular faces that connect the two bases. Face here, face here, face here, etc. If you take that prism and you turn it into something with circular bases, you end up with a cylinder. The same basic idea, except the prism has faces and edges and vertices. A cylinder starts with a base that's a circle and extends it into space like a prism does with this smooth, round, non-flat lateral face. If you start with a polygon and bring all the edges from the vertices of the polygon to an apex, you end up with a pyramid. You can do this. This one is a pentagonal pyramid because the base is a pentagon, whereas the faces, who all happen to be triangles, because that is true of every pyramid, comes up here. If you do that with a circle, you end up with a cone. Same idea as a pyramid, except beginning with a circle rather than a polygon. Something that is completely smooth all the way around and is more or less a circle turned 3D is called a sphere, the set of points that are all the same distance from that central point. And finally, a prism that has 6 faces that are squares is called a cube. So now we've been using this vocabulary for this entire video lesson, but haven't stopped to talk about what it means. A face is a flat surface of a 3D shape that is a polygon. So each of the faces in these examples of polygons, and I won't tell you, or excuse me, these examples of some polyhedra, some are not polyhedra, but in the example of the pyramid, for example, each of the faces, the triangles and the pentagon, were polygons. That is a face of a 3D figure. An edge is where two faces intersect. When you draw them, they look like lines. This is an edge from this pyramid. This is an edge from this pyramid. This is an edge of the cube, etc. And finally, where two or more edges intersect is called a vertex. Plural again, same as 2D shapes, are vertices. So where the edges intersect is a vertex, where the faces intersect are edges, and the faces are just polygons that form the outside of these 3D figures. So for the shapes on the next page, or for the figures on the next page rather, should not call them shapes, that's not correct, they are figures. You're going to, 1, tell if they're a polyhedron, 2, classify them if they are, or even if they aren't, and 3, you're going to try to number the edges, faces, and vertices of each of these shapes. Now, these are important properties of each of these polyhedra and otherwise figures if they're not polyhedra, but you want to try to number the edges, faces, and vertices. Go ahead. So for number 1, which is what we'll call the pentagonal pyramid in the top left corner. Pentagonal because its base is a pentagon. Pyramid because from the pentagon base, edges meet at an apex that in this case is above the base pentagon. So this pentagon has some faces, has some edges, has some vertices because it is a polyhedron. Now the pentagon base certainly is a face. And each of these triangular sections that jump up from the base and form and condense into the apex of the top, each of those triangular faces is also a face. So there's 6, 1, 2, 3, 4, 5 triangles and 1 pentagon, 6 faces, because there's 1 triangle for every side of the pentagon. Now there are 5 edges to the pentagon, 5 of them are which are already outlined in red, and each of the edges between triangular faces that reaches up to the apex is also an edge. So there are 5 north to the apex, and there are 5 in the pentagon, so that is a total of 10 edges. And finally, there are 5 vertices on the pentagon and 1 at the apex, is a total of 6 vertices. Now number 2 is a cone. A cone is not a polyhedron, so we cannot talk about faces, edges, and vertices because those refer specifically to polyhedra. But it's important to notice that this is a cone because it has a circular base. And like a pyramid, it meets at an apex. Number 3, also not a polyhedron because it has absolutely no flat surfaces whatsoever. This is an example of a sphere. And finally, for number 4, this is a prism because it has 2 bases that are identical, which are, in this case, hexagons. This is a hexagonal prism then. There's that hexagonal base, and there is one that is the same that I'll just color in here on the bottom. These 2 bases make it a hexagonal prism. So now it has some faces, some edges, and some vertices because every prism is a polyhedron. And so the number of faces, there's the 2 bases, which are already colored in green, but there are several rectangles, 1 for each side of a hexagon, that go from one hexagon to another. So 1, 2, 3, 4, 5, 6, 7, 8. 8 faces on a hexagonal prism. And we are going to jump to vertices next because they're easier to see. There are 6 vertices here for the hexagonal base that is on top at the moment. In our view, 6 vertices for the hexagonal base that is at the bottom right now, and that is a total of 12 vertices. And finally, for edges, we have 6 edges for each hexagon, as you can see that I'm outlining in blue right now. That is 6 and 6. And for each vertex on the hexagon, we have an edge that jumps to the other hexagon. So 1, 2, 3, 4, 5, 6 additional edges. That gives us a total of 18. So this polyhedron, a hexagonal prism, has 8 faces, 18 edges, and 12 vertices.